welcome to EPA's monthly webinar seminar series with the August 18th, obviously, talk titled Distribution Operation Options for Small Systems to Address DBP. So the good news is we're offering continuing education contact hours for this webinar. To receive such, you have to register at that email address down at the bottom lower middle address right here on the screen, if you would like continuing education credit. So the requirements of that are that you must be registered and you must attend for a minimum of 60 minutes. And if you are in a room with others that also would like the education credits, you need to provide those names to the address listed here under number 3. The webinars will be put up on the web. However, if you watch it on the web, we cannot give you a certificate for that, only by watching this live webinar can we give you a certificate. So again, we're done with the poll. So if you have more than one person in your room, please send that in the question box. How many people are in your room? That helps us document how valuable this webinar series is by totaling up the number of listeners. And one further note is that, yes, we will distribute slides, and we should have that out to you by the end of the week. So with that being said, our two speakers in order of presentation are Allison Dugan. Allison is an environmental engineer with the EPA's Technical Support Center in Cincinnati, Ohio. As a member of the agency's drinking water treatment optimization team for over 10 years, one of her primary responsibilities is to develop approaches for water systems to optimize their existing operations and infrastructure to control DBP formation in the plant and distribution system while not compromising other treatment objectives. The optimization tools and approaches developed by the team are field tested with small and to medium-sized water systems and then demonstrated to states that participate in one of the 4 regional area-wide optimization programs. The second speaker, who I'll introduce right now, is Dr. Jonathan Pressman. He's a research engineer with the Office of Research and Development's Treatment Technology Evaluation Branch, and also in Cincinnati, Ohio, where he has worked for also about 10 years. His research interests include characterizing natural organic matter in drinking water sources, with particular emphasis on DBPs, membrane processes for both drinking water treatment and natural organic matter concentration, and nitrification in drinking water distribution systems. He has a BS from Cornell and an MS and PhD from the University of Texas at Austin, and he is a professional engineer. So with that, welcome to our speakers, and we will start with Allison's talk first. Allison, you have the floor.
Thanks, Tom. As Tom mentioned, I am a member of the area-wide optimization team here in Cincinnati, and I'm going to talk to you today about operational strategies for controlling the formation of disinfection byproducts in distribution systems and things that we've become familiar with through our work through the optimization program. I'm going to start by presenting a little background on the area-wide optimization program and then talk real high level about DBP formation and what can be controlled to reduce DBPs. Then after talking a little bit about water quality monitoring, we'll get into some of the strategies that can be used to improve or maintain water quality in the distribution system. And throughout this, it's really important to keep in mind that what happens out in the distribution system can often impact other systems, especially if you're a system that sells water to another system or a parent system. So, but on the other hand, if you're a purchase system, a lot of the things that we're talking about today can apply to consecutive systems as well. So regardless of your role, one of the most important things is that water systems communicate with each other, especially water quality, which we find has not historically happened, and that's changing now as the regs are promoting that. So the area-wide optimization program encourages drinking water quality beyond compliance levels primarily through enhanced process monitoring and control using existing staff and facility facilities, so optimizing existing facilities. We also promote measuring performance relative to optimization goals, and we work hard to develop technical tools and implementation approaches which focus on improving or maintaining water quality, focusing on the multiple barrier approach. So in this case, we're really focused on the distribution system and keeping in mind that the residual in the distribution system is really the last barrier to public health protection before consumers drink your water. So the program began in 1989 with microbial or turbidity optimization at surface water treatment plants, and more recently has expanded to other areas, including the control of disinfection byproducts through optimization of treatment and distribution system operations. And that's what we're going to talk about primarily today. AWOP establishes water quality and monitoring goals as well as operational guidelines that are generally more stringent than regulatory requirements. And this is done to provide an increased level of public health protection to consumers, but also as a safety factor for compliance, for water system operators to keep in mind. We have established performance goals for disinfectant residuals and disinfection byproducts. But from the monitoring side, we also encourage paired residual monitoring, pH and temperature out in the system as well. We also have monitoring goals for frequency and locations throughout the system, which I'll talk about shortly, as well as operational guidelines for water storage tanks related to turnover time and mixing. So all of the strategies and field case studies I'm going to talk about today were developed in partnership with the AWOP states and the participating water systems. And just really quickly, I want to show a map which delineates or illustrates the extent of our national AWOP. Essentially, we have over 20 states participating, primarily from 4 EPA regions, and the program is supported by EPA and by ASDWA. And I just wanted to show this to offer some context to you all out there. It's possible that you are in an AWOP state, and that might be a resource as you're dealing with some of these issues as well. Okay, next I want to talk a little bit about DBP formation on a very high level. Essentially, what happens is free chlorine reacts with organic matter to form disinfection byproducts. Once these are formed, generally in the treatment plant, in a free chlorine system, over time, DBPs, especially THMs, will continue to form. And then in warmer water, DBP formation is often much higher than we see in cooler water. So I think the thing to really consider here is that the main parameter of all the parameters that impact DBP formation, pretty much the only thing that a distribution system operator can control operationally out in the system is water age. And that's what we're going to focus on today. So although this is not really to scale, this slide illustrates how the underground piping and the water storage tanks out in the system impact or add water age to the system. So water enters the distribution system and immediately begins to age, depending on how reactive or stable it is. And DBPs continue to form, residual will start to decay. And in this particular example, water travels to the first area for roughly a day, and then into the storage tank with 5.5-day turnover time. After leaving the tank, it passes through another area of the system and another tank and repeats this process until it gets to its final destination, which is a home near the end of the line. Based on these estimates of turnover time in tanks and potential water age, either due to larger underground lines or maybe low demand in those areas of the system, the water could be almost 3 weeks old by the time somebody in this home at the end of the line drinks the water. And 3 weeks is not uncommon based on what we've seen in our work. We sometimes see water tanks that have several weeks of calculated turnover time from one tank alone. So I think one of the things we really want to emphasize is that you shouldn't underestimate the impact of water age on water quality. Now I want to talk a little bit about monitoring, which means many things to different people. But really in the context of optimization, it means understanding what's going on in the system. So we use monitoring information or data to assess system performance relative to optimization goals or MCLs or whatever the objective is. But what we found through our work in working with systems to control DVPs is that often quarterly DVPs at compliance locations are not sufficient for really understanding the extent of the problem and the impact of a solution that a system may be trying to implement. And we also know, though, on the flip side, that DVP samples are expensive, so increasing the frequency beyond quarterly or at additional locations in the system can get really costly for a system very quickly. So we really promote using surrogate parameters for monitoring. And those include chlorine residual, pH, and temperature, all of which can be measured by an operator. And that water quality data or information is generally available immediately, opposed to sometimes it can take a few weeks for THM results, for example, to come back from a certified lab. So with having that data immediately, an operator can make decisions about what's going on in the system and whether or not there's an impact that's happening. So we really encourage through optimization to try to measure chlorine residual, pH, and temperature when collecting DVPs. We also promote through optimization more frequent monitoring than what some of the regulations may require, just to get a better understanding of the system. So we encourage monthly monitoring, and sometimes even more frequently during critical times, say hot weather. And we encourage monitoring at regular compliance locations, whether it's DVP location, TCR, whatever the location might be, to enhance the historical data and provide some additional baseline data. But we also encourage water systems to monitor at their entry point and at consecutive system master meters. Whether you're a parent system and you're monitoring the water leaving the plant and to the systems that you're selling to, or you're a consecutive system and you're purchasing water, it's good to understand what's entering the system. And then it's really important that those results are communicated among the systems, just so you can have an understanding of what might be happening in terms of water quality. We also promote monitoring from storage tanks while they're draining and other critical sites in the system. But all of this monitoring and all of this data collection is only valuable if something is actually done with the data. And I'm going to show a couple examples of that next. So this is one example of how collecting surrogate parameters, in this case free chlorine, can be helpful in assessing DVP formation. In this particular system, about 25 samples were collected, starting at the water plant effluent and working out to multiple locations in the distribution system. And then the data were plotted with free chlorine on the x-axis and THM concentration on the y-axis. And that allows the relationship between these two parameters to be better understood. And although this is kind of rough and it's going to change seasonally and is very system specific, it can provide some valuable information about potential THM formation. So, for example, in this particular system, when their residual is less than about 0.4 milligrams per liter, it might be concerning to them because historically their THMs have been around 80 or greater, and that residual level might be a trigger to go out and take a closer look at things. And for most of the systems, free chlorine systems that we've worked with, we've seen the lower chlorine residual is typically an indicator of higher THM concentrations, and chlorine residual is, for that reason, a very good surrogate for DVP formation. We've also seen, and I don't have time to show it today, though, sometimes elevated pH is an indicator of high THMs, and naturally water temperature is as well, so in the summer versus the winter in terms of THM formation. So if these parameters are measured in tandem or at the same time as the DVPs, you can start to develop that relationship and use those surrogates. Another helpful tool for systems is to assess areas of the system with potentially high water age that might be where there might be high water age, and develop a water quality map. And so in this particular study, we sampled throughout the system, starting at the water plant to get some baseline water quality data, and then throughout the system. And this legend is just indicating the chlorine concentrations that we measured throughout the system, over 1 to as low as 0 milligrams per liter. And so once the data is plotted on the map, systems can look more closely to identify what might be happening in these areas of the system. So for an example, this area over here is most likely influenced by these water storage tanks, and that could be the reason for the poor water quality in this area of the system. Other areas of the system might simply just have high water age because they're at the end of the service line or they're at some other isolated dead end or something like that. But once you have an understanding of what's happening spatially throughout your system, you can target areas with low residuals for operational improvements because most likely these areas with low chlorine residual have high THM concentrations. Okay. Now I'd like to talk a little bit about strategies that can be used to improve or maintain water quality in the distribution system, starting with water storage tanks. So if you recall a couple slides ago, we talked about how storage tanks can add significant water age in the distribution system. And sometimes that's due to tank design because, after all, they're designed for water quantity and system pressure and fire protection, not necessarily for water quality. Also, sometimes systems are not aware of how operational changes can impact water quality, but other times it's a hydraulic limitation that might restrict a system's ability to change tank operations. But in general, the first thing we generally do is try to encourage systems or work with systems to take a close look at storage tank operations and whether they are optimized for water quality. So there's two parameters that we think about in terms of water quality in storage tanks. And the first is tank turnover time, or water age in the tank. And basically that's the average time that water is in a tank. And it's really a function of how much volume is in the tank and how quickly the water flows in or out of the tank. The second parameter is tank mixing. And that simply describes whether the water is mixed or homogeneous versus whether the water in the tank is unmixed or stratified. And it's a function of water velocity coming into the tank and the duration of the fill cycle. We, through our optimization program, have established some operational guidelines for storage tanks. The first one related to storage time is to just maintain a low turnover time, less than 5 days, at all times, or establish and maintain a tank-specific water turnover rate. And that's kind of an important point because for some water systems, they can get away with a little bit higher water age in a storage tank because they have a relatively small distribution system maybe, and maybe they only have 1 or 2 tanks. But for other water systems where they have multiple tanks that water flows through before it reaches a consumer, 5 days may be too much. So that's kind of why we've set this up as an operational guideline rather than a firmer goal. The other parameter that we look at is maintaining good mixing at all times in each tank. And mixing we assessed using this performance ratio parameter, and our goal is to have the performance ratio be greater than 1. And that's simply an indicator of actual mixing divided by the desired mixing in the tank. So both parameters can be roughly assessed using a spreadsheet tool, but really, at the end of the day, it's water quality monitoring either at or around or in the tank that should really be done to confirm whether the tank is contributing to poor water quality, and before really any significant changes would be made to a tank. So the next couple slides, I want to show some examples of the impacts of tanks on water quality. And this first slide, the data was generated in partnership with the state of Pennsylvania. And essentially what was done is they used a string of temperature data loggers in this tank at a range of water levels over a couple-week period. And so temperature was measured at the top of the tank and then a couple feet down, all the way down to roughly the bottom of the tank. And as you can see here, the data loggers indicated that the tank was thermally stratified. And by definition, greater than 2 degree Fahrenheit difference is significant. And here in this tank, the temperatures ranged on average from low 60s up to almost 80 degrees Fahrenheit. So this definitely suggests that the tank was not well mixed. The second example is also from the state of Pennsylvania and demonstrates the impact of having both high turnover time and poor mixing on water quality. So in this case, there were 2 identical tanks side by side. Both tanks, each tank was a 250,000 gallon ground level tank. Tank 1 did not have a mixer, and so we estimated the mixing performance ratio to be about 0.33. And again, 1 is desired. Tank 2 had a mechanical mixer, and so we anticipated that the mixing performance ratio, assuming the mixer is working properly, is 1. And then we estimated the average turnover time in the tanks, in each tank, was 7 days. So this slide shows grab sample data from both of those tanks from the bottom of the tank to the top of the tank, and just showing chlorine residual. And tank 1, shown in red, which is the unmixed tank, is pretty stratified. The water quality coming into the tank was almost 1 milligram per liter, the residual. But then as we moved up in depth, or up in height really, to the top of the tank, we were almost to 0 milligrams per liter chlorine residual. On the flip side, the blue tank, the data shown in blue, tank 2, was well mixed, but recall that the turnover time in that tank was about 7 days. And so while the residual was consistent, it was only around 0.2 milligram per liter total chlorine concentration. So yes, mixed tank had a uniform water quality, but the high water age resulted in a low residual. So really, I think one of the take-home messages to emphasize here is that simply installing a mixer in a tank is not going to improve water quality. You have to have sufficient demand on that tank to have a water quality benefit from a mixer. And it's just something to be mindful of and not insurmountable. We'll talk about that in just a minute. So the last example I had to show quickly, a good example of low turnover time and good mixing in the tank. This was done in partnership with the Kentucky AWOP team, and we evaluated a 500,000 gallon elevated tank that had a mechanical mixer. And the average turnover time in this tank was 1.5 days. So low turnover time, well mixed, and the data, the water quality data supports that. We sampled from the bottom of the tank up to the top of the water column, and the residual was consistent, just over 2 milligrams per liter, and the temperature was consistent as well. So it is possible to have good water quality from tanks if it's well mixed and the turnover time is relatively low. So if you're in a situation where you don't have good turnover time, low turnover time, or a well-mixed tank, there are some things that can be done to address that and then in turn improve water quality. Operationally, water systems can work to reduce the tank volume, and essentially how that happens is the tank would need to operate at lower top level or lower bottom level or both to just generally reduce the overall volume of water in the tank. However, there's a lot of systems run into pressure constraints or storage requirements that might limit their ability to do this. Another way you can reduce the turnover time in the tank is to increase the fill and draw frequency. So essentially you're exchanging the same volume of water more frequently, but to do this you need to increase the demand on the tank. So that often involves maybe rerouting water or somehow adding a source of demand on the tank just to get it to exchange more frequently. There are design changes that can also be applied in the distribution system. Some systems have actually removed tanks from service if they have more storage than they need, or considered reducing line size. And so that may not necessarily be something that you go out and do right now, rip up the line and put in a smaller diameter line, but in planning you could keep in mind about maybe putting in a smaller line size as you're balancing water demand with water quality. On the mixing side of things, there are a couple operational strategies as well, mainly related to increasing the operating span, which will essentially increase the fill time or the time that the tank would mix during filling. You can also change the fill rate or duration, so essentially adding the same volume but changing the mixing intensity. So a faster rate over a shorter time or a slower rate over a longer time, I think will both have a positive impact on mixing. However, there are some operational considerations when you think about these strategies, not just balancing them, but also if the tank is thermally stratified, as we saw from that one tank a couple slides ago, that can prevent good mixing. And also, the simple placement of the inlet and outlet location can make mixing, operational mixing, impossible to achieve. So that's something to keep in mind as well. And there are design changes that can be done. Obviously, an engineered mixing system can be an option for some systems, or changing the inlet diameter to increase the inlet velocity can also be effective as well. Okay, next I want to talk a little bit about flushing and the impact that that can have on water quality. And I'm going to just focus today on automatic flushing and the benefits of an automatic flushing program. Essentially, it's a proactive approach, the way we apply it through optimization to maintaining water quality. It has a relatively low flow rate and a relatively low initial capital investment to implement. You see typically an immediate water quality improvement due to reduced water age. And we joke that we're actually creating artificial demand in the system by flushing and running these automatic flushers, but essentially that's what you're doing. You're creating a demand source, someplace for the water to go to keep the water fresh. And of course, this is going to increase the disinfectant residual, reduce disinfection byproducts, and often too, because it's done at a relatively low flow rate, so it doesn't cause discoloration and things like that, it tends to reduce customer complaints associated with taste, odor, and color. Of course, the flip side is you could have a customer complaint associated with dumping water on the ground, and you know, you have to be mindful of that as well. Several systems that we've worked with have reported just time savings or man-hour savings with auto flushers, whereas they used to just go out and flush when they had a water quality complaint. They installed auto flushers, and that saved man-hours, despite the fact that adjusting settings to target water quality does take some time, and we'll talk about that a little more in a minute. But, and generally, in the systems that have quantified this, we've seen a relatively small volume of water flushed can really impact water quality. And I'm going to show some examples of that next. So this particular system is a relatively large rural water system in northern Alabama. And they are a purchase system, a consecutive system. So every drop of water that they don't sell is lost revenue for them. And over the past several years, they've installed 14 automatic flushers, which run year-round. They are in northern Alabama. It doesn't get too terribly cold. And they run the flushers for variable lengths of time, depending on the water quality in that area of the system. Each of their flushers cost about a couple $100s to install. The flushing settings, the settings on the automatic flushers, so the duration and the frequency, are adjusted based on water quality at the flusher location, which they check on a monthly basis. So they have a water quality goal at each location, and if the residual that they measure at that location is higher than the goal, the operator will decrease the flushing volume. If the residual is too low when they check it, they'll increase the flushing volume. And that's sort of the process that they go through to optimize, and they write everything down, and they meter all of the water that they flushed, so they really kind of have a handle on things. And so I put in this table some information about the system, and really the take-home here is that the amount of water that this system is required to flush to maintain good water quality in their system, 0.5%, which is significantly less than either of their water loss rates, and really to them considered the cost of doing business. So this graph just shows some water quality data from that same system. And basically we just want to focus on the average chlorine residual over a couple-year period at their back-to sites increased as they were installing those flushers from about 0.65 on average to over 0.9. And again, that's attributed, this is system-wide impact on chlorine residual as a result of these 14 flushers in this relatively large rural system. Just getting that water moving can have a real impact on water quality. The other thing that might be of interest to some of our viewers is just the percent of samples that are less than 0.5 milligrams per liter. And those dropped off significantly as they implemented their flushing program. Similar results for THM formation, in that when the automatic flusher, so this is a THM site that is near one of the automatic flushers. It's not at an automatic flusher location. I want to be really clear about that, both for Alabama and from EPA's perspective. But again, we're seeing an overall improvement on water quality in the system from these flushers. And we saw it on chlorine residual on the last slide, and then THMs on this slide, where their goal is 70, and they were down well below that as they were implementing their flusher program. So when implementing this kind of program, the systems that we work with always meter the water they flush. The settings for the automatic flushers are determined based on water quality and adjusted on some frequency, usually a monthly basis. And although little water is flushed, when they quantify it, it's just, again, they think of it as the cost of doing business. And typically we see it's a few percent of what they're distributing, their distributed volume. So the last strategy I want to quickly talk about is rerouting water. That's a really system-specific strategy, but it can be effective. And basically, systems that have had success with this are just changing how water moves through the system through a combination of valving and rerouting and pushing water through differently. A couple examples here. One, a system was able to route through an area of low demand to end up at a high demand customer. In this case, it was a dog food factory, and I love that example because I remember it, and it's, I can see that. Yeah, okay, I can see how that's happening, yeah. Another example is the system had installed some parallel lines for fire protection. So larger lines with hydrants were in parallel to some smaller lines, and they were able to valve off and route the water through the larger line through the original smaller lines, which were tapped in for residential demand and to keep water moving. So I understand there's some constraints with this, and it might present some hydraulic challenges, and it's not something to be pursued lightly. But it has worked for some systems, and I think that's important to emphasize as we're sharing information about ways to improve water quality. And often, too, this needs to be done in combination with other strategies like managing tanks or potentially doing some kind of automatic flushing. So in summary, through our optimization program, we really, and working to control DBPs, we really promote monitoring to assess what's happening in the system using surrogates because quarterly DBP data sometimes is not sufficient enough to do so, and understanding water quality entering the water system. That's really important to know how to focus efforts and know what's happening and what kind of water you have coming into your system and what's happening then out in your system, and then doing something with the data to make it meaningful. So typically with the operational strategies, they focus on reducing water age. I mean, that's really what it boils down to, either by modifying tank operations or creating artificial demand or moving water around to impact water quality. And, these approaches may not completely solve the problem for all systems, but definitely they're lower cost approaches that operators can implement and a great starting point if you're struggling to control DBPs out in your distribution system, especially THM. So really quickly, I want to acknowledge the state of Alabama, Kentucky, and Pennsylvania and their optimization programs who provided a lot of the data that I showed today. And here's my contact information if you have any questions that we don't get to later on during the webinar.
Great. Thank you very much, Allison. As I mentioned earlier, we'll have questions after Jonathan Pressman's talk. So I noticed in the question box there are a number of questions that have come in for Allison, and we'll answer them later after Jonathan's talk. So if you have any questions for Allison, please put them in, and likewise for Jonathan as he's speaking. That will help us organize those questions. Also, if you missed the poll earlier in the when we started the webinar, and there are a number of people in your room, please put that into the question box. How many people are in your room? It helps us quantitate how well we are doing with the webinar series. So with that, I've introduced Jonathan earlier, so I'll just give the floor to Jonathan for his talk.
Thank you, Tom. Today I'll be talking about an aeration technology project that we did as a research project to address total trihalomethane's compliance for a small system. I'd like to acknowledge my co-authors of this presentation, Jatin Mistry from Region 6 EPA, and Amlan Ghosh and Chad Seidel from Corona Environmental Consulting. I'm happy to announce that Amlan Ghosh, who is the primary engineer on the ground conducting the project, is joining us to help with questions at the end of the talk as well. This was a large project funded through the U.S. EPA Water Environment Research Foundation Cooperative Agreement on Innovation and Research for Water Infrastructure for the 21st Century. That also involved the Water Research Foundation. It was a project team consisting of several consulting firms, Corona Environmental Consulting, American Water, Jacobs Engineering Group, and the Oto Missouri Tribe as well, with collaborators from EPA, the Water Research Foundation, and Oklahoma DEQ. Let's start with a little background. The Stage 2 disinfection byproducts rule has only recently become a requirement for small systems. This rule changes the calculation for compliance to a locational running annual average as opposed to the system-wide average that was previously used. This can be a more challenging constraint for many systems. Several years ago, my colleague in Region 6, Jatin Mistry, came to me with concerns about the Stage 2 DBP rule and small system compliance, particularly those with less than 10,000 customers, non-transient, non-community systems, and small consecutive systems. DBP data from Region 6 showed significant THM formation in many small rural systems treated waters, even before leaving the Clearwell. There were also many situations of small rural consecutive systems purchasing water from other small rural systems, where the consecutive systems have no treatment or means of lowering DBPs. Many of these rural systems are challenged to optimize treatment for DBPs because of limitations with water treatment plant equipment and the technical abilities and time of the limited operations staff. They need cost-effective treatment technologies with extremely low operator intervention. One such treatment, taking into account the volatile nature of THMs, is aeration. Aeration is a gas-liquid transfer process where the equilibrium condition, which is often represented by the Henry's law constant, and the hydrodynamic conditions, which include things like mixing and residence time, are exploited to transfer THMs from water to air. Aeration has been successfully used in distribution system tanks, but only rarely evaluated at the water treatment plant because THMs form over time and generally become more of a problem in the far reaches of the distribution system. HAAs are not volatile, therefore not amenable to aeration treatment. However, in discussions with Region 6, we found there were many utilities that had low HAAs and whose primary issues were THMs, therefore making aeration an appealing technology to assess. Therefore, the objectives of the project were to perform a comprehensive evaluation of formation and removal of THMs in a water treatment plant's clear well using aeration technologies. Conducting the project at the water treatment plant clear well was an important aspect of the project because the Region 6 data showed high concentrations of THMs before the water even left the treatment plant. And then to evaluate the feasibility of aeration technologies for helping small systems achieve Stage 2 DBP compliance, because it would be much easier for small system operators to maintain this simple technology at the water treatment plant, and because it would potentially solve the THM problem for multiple downstream small consecutive systems. Aeration has been demonstrated to have relatively low capital and operations costs compared with other THM compliance approaches and can achieve high levels of THM reduction. This table shows aeration technologies that were evaluated in this project with some key points. Of the technologies shown, spray and surface aeration systems have proven to be among the most cost-effective, lowest cost, and most energy-efficient technologies, and were the two technologies selected for further study in this project. In spray aeration, THM-laden water is pumped through engineered spray nozzles above the water surface in a tank. As the fine water droplets fall through the air above the water surface, the volatile THMs are transferred to the air. In surface aeration, small droplets of water are created by a floating surface aerator that is pushing water from a few feet under the water surface up into the air and across the surface to transfer the THMs to the air. With these technologies, tank mixing and ventilation is often incorporated and will be investigated as well. Other technologies that can be evaluated, but were not field tested in this project, include bubble aeration, packed tower and tray-type aeration systems, and membrane contactors. The first task in the project was the utility and site selection, evaluation, design, and permitting. Utility selection was critical to the success of this project. At the outset of the project, it was determined that the full-scale testing would be conducted in a reservoir located at a small, rural, or tribal utility with known THM exceedances, but no HAA exceedances. The utility needs to be located in EPA Region 6, specifically in Oklahoma. The first requirement was a utility that would be a willing participant in the project. Utility staff must have availability and be willing to provide support during the project. The Clearwell site needed to have the capacity for electrical loads required by the aeration equipment because installation of additional power service would not be feasible in the project budget. And it was desirable to have the utility located within about 50 miles of a major airport to limit travel time for the project team. Furthermore, there were necessary Clearwell requirements as well. These included that the selected Clearwell needed to have excess CT to allow for the addition of mixing without compromising the disinfection process and compliance. The storage volume needed to be less than about 3 million gallons, which would be most appropriate and ideal for this project considering the sizing and cost of the temporarily installed equipment. The ideal reservoir would have at least 2 sizable hatches to accommodate installation of mixing and aeration equipment, be operated at a near constant water level with at least 3 to 4 feet of headroom to incorporate aeration technologies, and be at ground level for easy access without a crane. Existing penetrations into the tank would be available for spray aeration and ventilation, and the reservoir would be physically capable of supporting the equipment. More than 60 utilities were evaluated during the utility selection process, resulting in the selection of the Otoe Missouri Tribe Water Treatment Plant in Red Rock, Oklahoma. The water treatment plant serves a population of approximately 250 and is supplied by raw water via a pipeline from Call Lake in Stillwater, Oklahoma. The water treatment plant process consists of twin microfloc trimite 50 units, which are adsorption clarifiers followed by mixed media filters with a coagulant polymer blend and sodium hypochlorite disinfection. The daily water treatment plant capacity is 115,000 gallons per day. From the water treatment plant, water is pumped into the clear well, which is a 20,000 gallon steel welded tank, 12 feet in diameter and 25 feet high. While not the ideal incarnation of the proposed requirements, the attributes were sufficient for installing both the spray and surface aeration equipment, and in a size and cost range within the project budget. This project was the first THM aeration installation to be permitted in Oklahoma, and the project team coordinated closely with staff at ODEQ. The utility selection process occurred in the winter and spring of 2014, followed by the initial design report submission in June of 2014. It took several months to get through the permitting process such that everyone was comfortable with the technology being tested. One requirement that resulted from the process was the need to move the chlorine dosing earlier in the process to provide additional CT to ensure Giardia compliance. It's important to note that while using aeration for THM reduction, you also need to be mindful of overall water quality objectives. As such, if aeration is implemented at a water treatment plant clear well, where CT achievement is critical, it needs to be ensured that the mixing due to aeration does not interfere with the CT objectives. In this case, additional CT was needed. The second project test was the installation of equipment and actual demonstration testing, which occurred between November 2014 and January 2015. The original project plan called for the demonstration testing to occur in the summer. However, with various contract delays, permitting, and a hard deadline on the contract end date, there was no choice but to conduct the project in the winter. This was beyond the control of the project team. Although less than ideal, DVPs were still sufficient to conduct a significant study. Primary equipment used in the demonstration testing included an Aqua Metrology Systems THM100 and a Parker THM analyzer, a PAX PWM 100 mixer, a Solar and Palau vent fan, a 3 horsepower submersible pump combined with 2 BETS TF spray nozzles, and a 2 horsepower Aqua Aerobic Systems AquaJet surface aerator. We acknowledge the contribution from all the equipment providers, including Aqua Aerobic Systems, PAX Water Technologies, Aqua Metrology Systems, and Parker Hannifin Corporation. Without generous contributions by these equipment providers, demonstration testing and THM data collection would not have been possible. The aeration equipment was installed and uninstalled live while the water treatment plant and the clear well were still online, in accordance with AWWA standards, by Midco Diving and Marine Services. Installation of equipment outside the clear well was performed by Haynes Equipment. The live installation was performed by divers who were in constant communication with field engineers via video feed. A photo of the Midco van with the video screen, recording, and communication devices is shown on the bottom right. Prior to the installation of the aeration equipment, the clear well floor was cleaned of all flocculated material, silt, sediment, sand, and any other accumulated debris. The spray aeration system included a Dayton 3 horsepower submersible pump and 2 1.5-inch full cone BETS spiral spray nozzles. The design parameters that influence THM removal efficiency include the water droplet size and air-water contact time. For the design flow rate of 84 GPM, it was estimated that about 50% THM reduction would be achieved at the clear well. With the surface aeration alternative, a floating surface aerator was installed in the clear well. A 2-horsepower aerator draws water and discharges it at a rate of approximately 690 GPM with an impingement or white water diameter of about 7 feet. Modeling results suggested that a power input of 2 horsepower would achieve approximately 60% THM reduction. The surface aerator selected for this application was designed with a collapsible float, shown here in the pictures, which allows the aerator to be installed and maintained through the existing 24-inch square hatch. In this picture are the THM analyzers. On the left is the Aqua Metrology Systems TH100 online THM analyzer. THM levels were monitored every 4 hours through this self-calibrating instrument. And on the right is the Parker THM analyzer, which was used for grab sampling and can measure THM concentrations in less than 30 minutes without tedious sample preparation. The testing period included the following test phases. The first was just baseline conditions, which was normal operations for the water treatment plant. Then we added active ventilation only, followed by tank mixing and active ventilation. Following that was surface aeration with both active and passive ventilation, and then spray aeration, engineered spray system with both active and passive ventilation. Each test phase was conducted for a 1-week period. The baseline condition was repeated at the beginning and at the end of the test period. Some test conditions were repeated in order to collect confirmatory data. Now let's begin looking at the data from the project, first with respect to water treatment plant operations, which will play a large role in the outcome of aeration at this utility. This figure shows the water treatment plant production, shown in blue, on December 1st and 2nd, 2014. Also shown in the figure are the start and stop times of the high service pumps, shown in red. Both the water treatment plant and the high service pumps operated between 7 a.m. and 5 p.m. on December 1st and were shut down overnight. This operational trend was consistent throughout the 2 months of the demonstration testing period. Generally, the water treatment plant was operated continuously and high service pumps intermittently during daytime hours only. From the perspective of the clear well, during daytime hours, the water level and water volume in the clear well are continuously changing. During daytime operational hours, the clear well level increases until the high service pumps turn on, which pump at a higher rate and lower the tank. This happens several times each day. However, the water volume in the clear well stays constant during evening and night hours until the next morning. This variation in clear well level and volume affects aeration because THM reduction is directly proportional to the hydraulic residence time in the clear well. During daytime hours, when either or both the water treatment plant and high service pumps are in operation, the average hydraulic residence time of water in the reservoir can be as low as 2 hours. At such low hydraulic residence times, there's not sufficient formation of THMs within the clear well to be removed. As such, the performance of any aeration system in THM removal is likely to be less than optimal under these conditions. For reference, here are some water quality parameters in the raw and treated water during the study period. Of primary interest are that the water temperature was below 15 degrees C and only a small fraction of TOC was removed during treatment, leaving the remainder to interact with chlorine and form DVPs. Now let's move on to the THM concentrations in the water treatment plant effluent and the clear well effluent during the week-long baseline testing period. The THM concentrations in the water treatment plant effluent, shown in orange, varied between about 60 and 100 micrograms per liter during the baseline testing period over the course of this week in November. The THM concentrations in the clear well effluent, shown in blue, varied between about 120 and 180 micrograms per liter during the same period. This shows that the THM formation reaction is incomplete in the water treatment plant effluent, and THM concentrations increased between 30 to 60% in the clear well. A closer look at the THM concentrations in the clear well effluent shows kind of a sawtooth effect, meaning that there's daily trends of gradual THM increases occurring at night, followed by a sharp decrease. It was observed that the THM concentrations in the clear well increased at night with increased detention time in the clear well. Remember, there's no pumping into or out of the clear well at night. This was followed by a sharp drop in THM concentrations the next morning, initiated after the water treatment plant began producing water the following day. The fresh water had considerably lower THM concentrations, resulting in dilution of the THMs in the clear well. The daily pattern of THM formation and dilution was pretty consistent over time, resulting from the daytime-only operations at the treatment plant. After the baseline THMs, let's look at spray aeration with active ventilation. A similar sawtooth effect in the clear well effluent THM concentrations is observed here, and there's two factors that are causing it. The first factor is the same as with the baseline testing. When the water treatment plant is switched on every morning, the fresher water with lower THM concentrations enters the clear well and dilutes the overnight water in the clear well that has higher THM concentrations. The second factor is an artifact of the location of the THM sampling port, which is on the pipeline between the clear well and the high service pumps, and was our only access point for this sample. So unfortunately, during overnight hours, the THMs are not representative of those in the aerated clear well itself. When the high service pumps are switched on the following morning, the overnight water is pumped through the high service pumps, and the THM concentrations measured represent THM concentrations in the clear well with the spray aeration system in operation. Given these factors, there's a difference between THM removal by the spray aeration system and overall THM reduction through the clear well. A different approach needed to be adopted to understand the actual THM removal by the spray aeration system. But first, to more visually quantify the overall THM reduction through the clear well as a result of the spray aeration system operation, both with and without ventilation, this figure shows a box and whisker plot that compares the overall THM reduction with spray aeration with active and passive ventilation to the baseline conditions. In this plot, the median THM concentration is represented by the interface between the orange and gray box. The bottom of the box is the 25th percentile. Excuse me for a sec. The bottom of the box is the 25th percentile. The top of the box is the 75th percentile, and the whiskers represent the minimum and maximum values. So the median THM concentration was 100 micrograms per liter here, 100 micrograms per liter for spray aeration with active ventilation, and 106 micrograms per liter for spray aeration with passive ventilation. This compares to, This compares to a median THM concentration of 135 micrograms per liter during baseline conditions. As such, spray aeration with active and passive ventilation results in 26% and 21% overall THM reduction compared to baseline conditions. While there are some limitations to the data analysis, as described in previous slides, the figure shows that with spray aeration, active ventilation is only marginally more effective than aeration alone. In order to decouple the different THM formation and removal mechanisms, a different analytical approach was adopted. Several assumptions needed to be made to perform this analysis. These assumptions included that THM data recorded during daytime hours were excluded because of the continuously changing hydraulic residence time. Night samples taken from the pipe between the clear well and high service pumps represents the THM formation without aeration because the plant is not pumping water and the pipeline samples are not aerated. Data shown in blue on the figure is the last night sample before the morning pumps turn on. When the high service pumps are switched on in the morning, the first sample collected and analyzed by the online analyzer represents the water quality that was present within the clear well and was impacted by the aeration system. And this data is shown in orange on the system, on the figure. The percent removal, which is essentially the difference between the blue and the green data, is shown in gray on the figure. Based on this analysis, it can be inferred that the spray aeration system with active ventilation removed approximately 34% of the THMs from the clear well. Now jumping ahead to surface aeration. The raw data figure for the surface aeration was similarly sawtoothed as the figure shown for spray aeration. So fast forwarding to the overall reduction of THM concentrations through the clear well during surface aeration can be summarized similarly in a box and whisker plot. The median THM concentration with surface aeration with active ventilation was 108 micrograms per liter, and with passive ventilation was 107 micrograms per liter. This compares back to the median of 135 micrograms per liter during baseline testing. As such, surface aeration with active and passive ventilation result in about 20% overall THM reduction compared to baseline conditions. Compared to spray aeration, the overall THM reduction through the clear well during surface aeration was slightly lower. Slightly colder water temperatures during surface aeration compared to during spray aeration could have contributed to the reduced effectiveness of the surface aerator. A similar approach to the one described for spray aeration was adopted to estimate THM removal achieved by the surface aeration system, with maximum overnight THMs shown in blue and the first flush morning THMs shown in orange. Based on this analysis, it can be inferred that the surface aeration with active ventilation removed 22% of clear well THMs. In addition to overall THM reduction, insights were also gained on individual THM speciation. With the differences in volatility and diffusivity of the 4 THMs, what happens to the speciation from chlorination through aeration? The first bar shows the water treatment plant effluent, with larger amounts of chloroform forming early. The second bar shows the baseline conditions before aeration was started. Given some time in the clear well, all of the constituents increase. Chloroform shown in gray, dichlorobromomethane and dibromochloromethane represented by X2 in the figure, and bromoform shown in blue. Finally, after spray aeration, all of the THMs decrease, with chloroform decreasing the most, followed by bromoform. The main reason for including this data in the presentation is because it is often assumed that because the volatility of bromoform is so much lower than chloroform, that aeration may not be effective for situations with significant bromoform concentration. And this data shows there are other factors involved, and bromoform can be successfully removed via aeration. Summarizing aspects of the project, both from data in previous slides and from data I was not able to present because of time limitations, both surface and spray aeration lowered clear well THM concentrations between 19 and 34%. The lower removal compared to planning was likely due to lower water temperature during the study compared to that assumed during the planning. THM removal by aeration is not equal to overall THM reduction achieved within the clear well because of various factors including the sampling locations, hydraulic residence time, and intermittent operation of the water treatment plant. Both mixer and active ventilation by themselves resulted in marginal reduction of THMs in the clear well. Aeration by itself will not result in achieving sufficient THM reduction for stage 2 DBPR compliance in the Otoe, Missouri Tribe water system. And both field measurement instruments for THM analysis yielded results within plus or minus 10% of laboratory results. So finally, a little guidance on aeration implementation. Prior to evaluation of any treatment technology or management option, the extent of the DBP problem needs to be understood. One takeaway message of this project is that aeration technologies remove THMs from water, but they do not alter THM formation potential of the water. So if there's additional organics and chlorine left in the post-aerated water, THMs will continue to form. Aeration technologies can only be installed in water treatment plant clear wells or distribution system reservoirs. So the relationship between the location of the clear well reservoir and the stage 2 DBP sampling sites in terms of water age and THM reformation needs to be established. This sets some practical limitations on both the highest THM concentrations where mitigation by aeration is feasible and locations where aeration technology can be implemented. The concept is illustrated here with a hypothetical water utility. Assume that the x-axis represents all the sampling locations in the utilities distribution system, starting with the water treatment plant at the extreme left and the stage 2 DBPR maximum hydraulic residence time sites at the extreme right. The sampling sites A, B, and C are arranged by increasing THM concentrations. The y-axis shows the concentrations, and the green curve represents the THM concentrations at the various sampling locations. Aeration can be implemented at any location at the water treatment plant or in the distribution system. Ultimately, removal of X is required to stay below the MCL. In order to stay in compliance, X THMs need to be removed no later than site C. theoretically, aeration could be installed at sites A, B, or C. However, at site A, 100% of the THMs would need to be removed, and systems are not typically that efficient. This leaves site B or C. Because site C requires a lower percent overall removal of the THMs present at that location, it would likely cost less to remove the THMs at that location as opposed to site B. While this project was designed to specifically study the removal of THMs at the water treatment plant Clearwell as a means of hypothetically helping multiple downstream consecutive systems, it was a learning experience in that we became sensitized to the high percent removals and residence times that would be required to achieve those removals so early in the THM formation process, the equivalent of trying to use aeration at site A on this figure. Finally, just to acknowledge several other individuals, the Water Research Foundation Research Manager, Kanan Ozikin, the Project Advisory Committee that included Bob Raxo, Mao Fang, and Bob Praga, the Oklahoma DEQ, and the Oto-Missouri tribe, specifically Rich Graff, and finally some contact information. Thank you very much.
Okay, thank you very much, Jonathan. And now it's 3 o'clock. I hope you can stay with us for a little bit of questions. We can stay for a bit of a time, up to 3:30 perhaps, if we have questions. A number of questions have come in. Keep sending them in, and we'll try to keep a handle on it. But first, if we go to the next slide, if you have to go, thank you for attending our webinar. Listed here are the remaining webinars on the schedule for the rest of the calendar year. And in last week of September, we'll have a webinar on UV disinfection systems. So, on to the questions. The first one is for Allison. So if this is a little bit of a long question, but if a system is using artificial demand flushing instead of automatic flushers, is there a minimum amount of time a system should wait before they take their DBP samples after flushing? This person is concerned that the system could get lower DBP compliance samples that aren't reflective of the typical water quality their customers are receiving.
And I want to say I share that concern, and I think all of the AWOP states, the states that participate in our national AWOP share that concern, because basically then you're gaming the system. I mean, we look at those semi-permanent installations of automatic flushers as regular treatment for a water system, whereas spot flushing or flushing before you collect the sample, your DBP sample the week before or whatever, is probably not considered regular treatment or regular operations of the system. So that is something to be concerned about, and really the focus should be on improving overall water quality in a distribution system consistently, not just around the time of DBP sampling. Good question, thank you.
Okay, thank you, Allison. Here's another one. Won't the addition of initial free chlorine cause greater THMs, total THMs? So would it be better to plot chlorine degradation percentage instead of plotting residual chlorine as the initial amount of free chlorine added affects total THM formation?
Those are excellent points and all valid. And I think the emphasis is really on working with the data. When we first started working with ways where we could look at the data, present the data that we collect when we do an evaluation for a water system to the water system and what tells the most effective story, we did look at plotting degradation or decay against THM formation, and it just got to be a little bit more of a confusing concept, but your point is excellent and very valid. So I think the take-home is just about when you collect those indicator or surrogate parameters with DBP samples, whether it's chlorine residual or pH or temperature, do something with the data to make it meaningful so that you can kind of understand what kind of trend you're seeing with those surrogate parameters relative to THM formation.
Okay, great. The next question is for you, Allison. Another one. Are you also looking at chloramine residuals and HA5 formation?
We are. I'm glad you asked about that, because it gives me a great opportunity to acknowledge one of my team members. We have a 5-person optimization team here in Cincinnati, but Matthew Alexander, one of our team members who I was remorse in acknowledging earlier, he has partnered with us on a lot of the work that I showed, and he is leading the effort on the chloramine optimization stuff that we've been developing and approaches we've been developing. It's not quite as far along as the free chlorine work looking at DBP control, but we are looking at sampling in chloramine systems, what kind of parameters we would measure, what those parameters might tell us about nitrification. We do know that nitrification is really impacted by water age in the distribution system, or can be, and so there are a lot of similarities in the approach that we're taking with the chloramine system. So yes, we're looking at chloramine optimization and what that means and what that would look like and what parameters an operator or water system might monitor for to assess their performance. In terms of HAAs and optimizing for those, it's not so much of a water age issue. What we've seen, at least, is more of a treatment kind of challenge. And we also have a treatment optimization program where we look at optimizing within the water plant or within the treatment process to control DBP formation. So in a situation like that, we would probably go back into the plant, which I didn't have time, nor was that the focus of today's presentation, and look at ways to reduce HAA formation through the treatment plant. So good question. Thank you.
Okay, great. And one more, and then we'll go to Jonathan. One more for you, Allison. What are the surface water implications of flushing chlorinated water into the storm drain?
I'm going to say that that varies by state, but not to be overlooked. So typically, the automatic flushers have been set up, and the systems that we've worked with have been set up in areas where the chlorine residual is pretty low. So for the most part, you're flushing water with a very low residual out eventually into the storm drain. You know, and as long, a lot of states that we've implemented these programs with have been of the mindset if we're not flushing into a stream or a body of water, then it's probably okay. But others have taken the approach that that water needs to be dechlorinated, even if the residual is very, very low. So that's definitely something to be mindful of, and something I didn't have time to get into today during the presentation. But there can be implications related to flushing chlorinated water and discharging it, as you mentioned. So thank you for that, making that good point in that question.
Great. Thanks, Allison. Now a few questions for Jonathan. Can you explain the potential for HAA5 formation increases after the installation of aeration systems?
So what we know about HAA5 or haloacetic acids is that they're really not very volatile. So implementing aeration in the tank doesn't really have much of an effect on the HAAs that are there. So they're neither going to be created or removed. And so we don't expect much of a change. Even though we didn't measure them in this study, we don't expect much of we didn't measure them before and after treatment. We don't expect much of a change due to aeration.
Okay, great. Another question, how do you think that results would have been impacted for your Oklahoma Tribal Total THM study if the testing period would have been scheduled during much warmer summer months instead of the December-February period that was utilized?
Yeah, that's a good question. You know, we had initially planned to do this in the summer, and unfortunately, to a host of factors, as I described in the talk, we were forced to do it in the winter, really because of the contract end date. And so the project had to be completed or not done at all. Now, we believe that DBPs would have been higher in the summer than in the winter. However, at the same time, because we had to change the chlorination point to earlier in the process for CT for Giardia in this study, we were adding more chlorine earlier in the process, and that sort of tended to artificially raise the DBPs during the winter months. And so, as you saw in the presentation, it gave some pretty high DBPs for us to look at and look at removals. And those were probably, I think, fairly typical, perhaps, of summer months under normal operating conditions.
Okay, great. Did the surface aeration, this is for Jonathan, did the surface aeration occur with lower temperatures than spray aeration?
That's correct. So the the surface aeration had the temperature, we were in the winter, the temperature was slightly lower during surface aeration than with spray aeration. And we attribute perhaps the lower removals of surface aeration were in part perhaps due to these lower temperatures.
Okay, and another for Jonathan, and then we'll go to Allison. How do you know ahead of time and or determine afterwards how much CT might be affected by mixing aeration?
I guess at this point I'd like to ask Amlan to jump in and see if he has an opinion on this one. Amlan, did you know ahead of time or determine afterwards how much the CT might be affected by mixing in the aeration in the project?
Yes, this was because this was a full-scale installation. We had to, in order to get the aeration system permitted, we had to run those calculations. The short answer is we did not necessarily determine what CT we were getting or would have gotten. We assumed the most conservative scenario. So what we assumed was when an aeration system was installed in the stairwell, it would be quote-unquote completely mixed, meaning that the baffling factor we assumed was the lowest that baffling factor could be, which was 0.1. So, and that is the reason, as Jonathan mentioned, we had to move the point of chlorination, given the fact that this was a small water treatment plant with a package treatment system, and previously they were only using that clear well to get the 1 log Giardia credit. There wouldn't have been sufficient CT credit in the clear well alone. That is why we had to move the point of chlorination to the raw water so that we could claim that additional time of the water passing through the treatment units and the pipelines before it gets to the clear well, so we have the necessary 1 log Giardia CT.
Okay, great.
Thank you, Amlan.
Thank you very much. Okay, so this one's for Jonathan. Were any TOC samples taken to look at precursor levels around the clear well? Also, were any samples, including DBP, in the distribution system?
So we took TOC samples, and I showed that in the table in the presentation. The TOC, I'm flipping towards that. The TOC of the raw water was between 3.5 and 3.7 milligrams per liter, and in the water treatment plant effluent, it was 3 to 3.1 milligrams per liter. Was there a second part to that, Tom? Also, were any samples taken in the distribution system? Amlan, did we take distribution samples in this project? I don't recall.
Yes, there are two. It's a little complicated again there. We did look at distribution system samples. Unfortunately, we did not collect those samples as part of our project. However, the utility collects their quarterly compliance samples, and we got those data, and we tried to correlate them with the DBP reduction in the treatment plants. The reason we do not present the data either here or in the report was that there is a very high amount of hydraulic residence time in the system, and we were only, for any given test condition, we were only running that test condition for about a week, or about 7 days. So it was very difficult to correlate when we looked at the distribution system THM data, to correlate that with the water that was treated with surface aeration or spray aeration or mixer. It could have been any of those above conditions. So that is why we did not include those in our analysis. But we do have, the utility did collect the distribution system DBP samples during the testing period.
Thank you.
Thank you very much. This one's for Jonathan. Did you look at energy costs of aeration, mixing, venting? Which was the most cost-effective based on the removal performance you observed?
And Amlan, this is another question for you. Did we measure the energy costs?
Yes, we did. What we did was we looked at the total electricity cost, not the cost, the total electricity consumed during this study. I would add that in addition to this particular study, there have been other studies done, other research foundation projects, as well as other work that we have done, which looked at that energy question more effectively or more closely. One of the things between choosing, ventilation versus mixing versus aeration is what your objectives are going to be. Mixing will, like Allison was presenting in her presentation, mixing will mix the water, but it will not necessarily remove THMs from the water much. So depending on where you are setting up these systems, whether it's mixing or aeration, and what your objectives are, you have to take that into consideration for a cost-effective, like the benefit-cost ratio calculation.
Thank you.
Okay, great. And just another question about costs. Are cost models available for these technologies? Was it part of this project?
So we didn't do, as far as I'm aware, we didn't do cost models for this project. So I don't think, as part of this project, any are available.
Yeah, no, we did not develop cost models as part of this project.
Okay, and here's a question for you, Allison, regarding can you measure THM formation potential in real time? This person's data shows a large daily variation across the system. And how do manually sampling capture that impact?
And that's a good point. When you grab sample, you collect grab samples, it's hard to really, you can't capture that kind of variability. In some other studies that we've done, I didn't show any data from that today, we have done some continuous monitoring with chlorine analyzers, but we have not used any, I don't have direct experience with the online THM monitors, but I do believe they're out there and available for systems if they want to use them just for process monitoring type applications.
Okay, and here's another one for you, Allison. Oops, here it is. Is it possible to establish a relationship between total residual chlorine and TTHMs in the system that uses chloramines?
That is a good question, and the relationship is not as clear in the systems that we've worked with. But the other confounding thing or thing to keep in mind, really, is that in a chloramine system, and Jonathan can correct me if I'm wrong, I believe that you don't typically have a lot of additional THM formation once the ammonia, the chloramine, is added to the water. I mean, 10 to maybe 20% is kind of like a...
There's some further THM formation, but it's not nearly as large as in a free chlorinated.
Right. So when we do our chloramine optimization work, for example, we don't necessarily focus in too much on THM formation other than what's leaving the plant, and maybe at the stage at the DBP compliance locations. There we're looking more at some of the other indicator parameters related to nitrification and those kinds of water quality challenges.
Okay, great. Thank you. Hang on, I had my question, but then the screen flipped. So I apologize for that. Okay, this one's for Allison. What drives an AWOP team formation within the U.S. EPA region? Why are there no AWOPs in Region 5?
Well, we don't currently have an AWOP in Region 5 because we just haven't had the stars align and the people in place to just make that happen. I mean, I think if there's interest within EPA Region 5, either the staff or manager level, get in touch with us and we can talk more about that. And, we just, unfortunately, being in Cincinnati, it'd be great if we did have a Region 5 AWOP, but our closest partner right now is in Region 4. But I would encourage whomever asked that question to be in touch if there's some interest there.
Great. And your contact information is on the slide.
Yes, it is.
This one's for Jonathan. What was the estimated turnover time in the tank? Was there any concern with the tank being influenced by the previous week's aeration treatment technology?
So during the daily operation periods of the tank, the hydraulic residence time in the tank, or the turnover of the tank, could be on the order, or was on the order of just several hours. So there really wasn't any concern from a week-to-week basis of the effect of one treatment technology being carried over to the study of another.
Okay, great. And I think this is our last question that we can get to. Are there any, and this one's for Jonathan, so you looked at it in terms of tanks and clear wells. Are there any of these aeration strategies available for domestic hot water systems? DVPs can be a problem for sites that use secondary disinfection.
So I guess I've never really considered doing something specifically on a hot water system. If you're talking about domestic hot water, those are typically tanks in homes. I believe that's what this is being asked.
Or perhaps they're talking about large buildings like hospitals or casinos and things
So,
like that.
all right. So if the hot water, again, is done in boilers or in tanks, there's typically not a headspace. In some form or fashion, one has to transfer the THMs using aeration from the liquid to an air or to the headspace. And so without that in the current system, there's not a whole lot of way to do it. Without breaking head in the system and having to repump. There is the option of using membranes to do that, although I don't know that I'm not aware of anyone having considered that for hot water systems before.
Okay, and it could lead to other issues like Legionella and things like that.
Perhaps, yes.
Yeah. Okay, well, that runs out to our questions. So thank you so much for attending our monthly webinar series on distribution operation options for small systems to address DVPs. Thank you for our speakers, Allison Dugan and Jonathan Pressman. Outstanding presentations, and I hope to see you next month, or that you're able to attend next month's webinar, September 29th, on UV disinfection systems. Thank you again for attending. Bye-bye.